So I will be doing goal test in this particular manner, checking out every constraint, whether it is satisfied or not, whether the values that I replace the state with, do they actually give enough, do they actually violate any constraint, or they do not violate any constraint. So that is the way the goal test is defined. This is again a difference between a CSP and a standard search problem. The standard search problem state, since it was a black box, we just were comparing current state against the goal state, and that yielded us the goal test. Now, but the goal test is much more complicated, I should say, or rather much more definite. Should also say it is much more definite, because I have to do certain activities over there to check every constraint and then say that, okay, since all the constraints are matching, this particular state passes the goal test. Otherwise, I say the goal test is not passed. So this is how we kind of check or see the differences between standard search problem and CSP. Okay, simple example of a formal representation language, I don't know, allows useful general purpose algorithms with more powerful than standard search algorithms. Okay, we will talk about this later. I don't get myself the meaning of these 2 points, but we'll talk about these 2 later and revisit this slide. So now I'm jumping on our first standard problem called as map coloring problem. And this map coloring or graph coloring, as they are called with both the names, map or graph. So I may have a graph that I want to color, graph of nodes I want to color, or I have a in real world sense a map given to me of a standard country or a province or a state, and there are regions of the state defined, and I want to color it. So that's a very simple problem. So what exactly is the problem? You see in front of you a map of Australia divided into the territorial regions of Australia. There are 1, 2, 3, 4, 5, 6, 7, 8 regions, including this Tasmania, which is away from the mainland Australia. But the problem here is that when I'm coloring this map, I have a fixed palette to me. I want to decide what number of colors I should choose such that I could color this graph, and the constraint put on is no 2 adjacent regions should be colored with same color. The next constraint that is put on is the color palette should be of the least size. So there are 2 constraints here. I want to color this graph using minimum number of colors such that no 2 adjacent regions are colored with same color. So you can think of this problem as a very easy problem that way, but then it's a very challenging problem as far as the algorithmics are concerned. So again, a toy problem. Maybe you can't say that it's a real world problem, but it matches to many real world problems in the way it is represented. Okay, so we are learning map coloring problem because we want to learn how does a CSP problem is formally represented. That is what they were saying over here. Formal representation language. How should I formally represent a CSP problem? Is there a useful general purpose algorithm that I can use to solve a CSP problem? So the definition of CSP problem, which we should call formal definition, should be in a way designed such that there will be certain algorithm that will facilitate with the definition of the problem. Okay, जो definition मैं formally represent करूँगा CSP, जिस definition से मैं CSP को represent करूँगा, it should facilitate me in solving the CSP problem, and that is why those 2 points were discussed in the earlier slide. Okay, even I'm confused about those 2 points. Don't worry, I'll come back after making you aware what this problem is. So English definition of the map coloring problem you understood. So I will be given some map. In the map there will be certain regions, and the regions will be such that some of the regions are adjacent to other regions, and some of the regions are disconnected. Something like this particular map that you are looking at of Australia, where there are 8 regions. Some of the regions are tightly connected to the other region. So if you see this South Australia SA region, you'll find that it is connected to 1, 2, 3, 4, 5 adjacent regions. Okay, so if I choose a color over here to color with this particular region, then same color can I use in the other regions? No, I can't use the same color in the other region. So this is how these constraints play off when you try to identify what colors I should use to color this. Now, one instance of this problem is where we have been given the palette, the color palette. In this case, we have been given the color palette. So color palette is this. So we already know that we want to color this graph with 3 colors. So this is one instance of map coloring problem that is defined differently. So here we are not asking we should use minimum number of colors. Instead, we are saying that the maximum size of palette is 3. So I should achieve this in 3 or less than 3 number of colors. This is what the problem is now. Okay, so such variations in the definitions will always be there with these standard problems. Okay, but in general, the map coloring problem, I guess you have understood what it is. Now, to represent this map coloring problem, we need to understand these 3 facets or these 3 aspects of definition. Just like we had those 5 things to define a state space search problem, here we need to understand these 3 things first. The first thing is variables. What are the variables using which I could be able to define the state of the problem? Now, what is the state of the problem? State of the problem in map coloring problem would be any region getting a particular color from its domain. Okay, so I will be having to represent a single state. To represent a single state here, I will be having a vector like this of 8 units, where first unit would refer to first region, second unit or second bit would refer to second, third, fourth, fifth, sixth, and seventh. Okay, there's 6 or 7. Why I was counting 8? Did I miss any region? Numbering is wrong. 1, 2, 3, 4, 5, 6, 7. Sorry, in Australia there are only 7 regions. I somehow added my own region into the map. Okay, somehow I miscounted the things. It happens when you are in the afternoon lecture and you had a good deal of lunch. Okay, so there will be 8 values here, and this single thing would represent the current state of map. So a properly colored map would have every region colored with some color. Okay, so a properly colored map would have 7 different values in this state representation. So maybe something of this sort. I may have R, G, B, then R, then again an R, then again an R, maybe G, something like this. So 1, 2, 3, 4, 5, 6, and lastly I may have another color to the last region. Okay, now the question comes, if I'm representing state of this map using this particular notation, so this is some state I for my map coloring or graph coloring problem. What I'm going to do is, what I'm going to check is, when I'm doing a goal test, is this value that I've selected for this variable, first variable, is this value from the domain? Yes, it is from the domain. Okay, fine. Then this will be done for all the 8 values, all the 7 values. Second thing we should do is, does it violate the constraint of having same color to 2 adjacent regions? For instance, region 1 and region 2, they are adjacent to each other. So color I used for region 1 coloring should not be used for region 2. Okay, so I just check. So region 1 is red in color, region 2 is green in color. They are of different colors, so they are consistent with the constraint that I have. Okay, similarly, region 1 and region 6, if I check, so 1, 2, 3, 4, 5, 6. Okay, luckily region 1 and region 6, they are also of different colors, so they also satisfy the constraint. But region 2 and 6, they both are of same color, and since this happens, this state is, although a complete state representation of my problem, is not a consistent one, and hence it's not a solution to my problem. Okay, so this is exactly how these map coloring problems try to represent a state. So one state is collection of instance values assigned to variables using which the state is defined. Now in constraint satisfaction problem, we are also allowed something of this sort, where I have this 8-bit representation and there are certain values in this 8-bit. They are not assigned any, certain variables are not assigned any values. For instance, these two variables in this assignment are not having any values. R, G, B, 3 is there, 4, 5, and maybe 7th region is R. Okay. So if I see this particular assignment, you'll find that this assignment is incomplete because two of the variables that define your state, okay, they are not having any instance value. They are not having any instance value. Okay, what about satisfying the constraints? As far as the rest of the variables are concerned, we will check whether they are satisfying the constraint. If they satisfy the constraint, the incomplete state representation might still be a consistent one. Okay, so partial state representation is there, but it's not consistent, or but it may be consistent. It all depends on whether it follows the constraints or not. So in a way, when I'm representing the problem, if I want to use this lingo or this kind of representation of the state, and this way I want to represent a state and then use this information to solve the problem, I should be able to define three things. Number one is, what are the variables that define a state, that define a complete state for that matter. Okay, then I should know what are the domain or domains of the variables. So in this case, all the variables may be having same domain or different domain. As far as graph coloring problem is concerned, all the variables have same domain. That is, I can choose from the same palette the color that I assign to a particular region. Third thing that I need to define is, what all are the different types of constraints that the problem definition poses on a state being consistent. Okay, so the constraint here is adjacent regions must have different colors. So whenever I say adjacent region must have different colors, I must represent. So if this is the way I'm representing the variables, my constraint will be WA and NT are adjacent. So WA color should not match to NT color. Okay, so this variable, although it reads WA, it is not representing the region. It is representing the color this region has. So WA may have value between R, G, and B. So I hope this is clearer to you. Okay, and I have conveyed the right meaning and not the confusing meaning. You are not confused at this point in time. Okay, because I'm not able to see your faces, and it's very difficult to judge after saying few things whether you have understood or not. So just a sanity check. You have understood what map coloring problem is? If so,